Hello everybody. Here's another video. This one's going to be on optimization, which is really neat because it's actually applying to real-world situations, though simple, the techniques that you've learned from calculus and derivatives on how to make the best of a situation. Optimization is it means to find the best solution when you have limited resources. And really that's what it's about. You're always going to have in the real world in applied math, you're going to have a restricted domain, like your values of x are going to be between 0 and something else, so that you're not looking for just any possible number, but you're restricting your set of numbers, and you want to find of that set which is the best. This is a huge part of actually using math to help businesses and things like that. So the strategy to follow, that's another thing I like it, because this is not just use this formula or follow this procedure. You really have to kind of think a lot and see what's sensible, and not just follow a robotic routine. So you want to identify all the given quantities. So identify all given quantities. Um, and all quantities to be determined. Okay? So for example, if they give you the perimeter of a figure, then you write that down, p equals whatever. And if they say you have to find the area, then you write down a equals, and you try to write down a formula for that. All right, 2. You write a primary equation. Okay. This equation, whatever it might be, this is to be optimized. Optimized meaning maximized or minimized. You're trying to you're going to take the derivative of that and set it equal to 0. I mean, that's basically it. Secondary equation is really there because you need to reduce this to be an equation of one variable. This primary equation, they're going to give you an equation of multiple variables. So secondary equation is given so that you can reduce primary equation to one variable. Okay? And then determine domain. All right? And that's going to come from your secondary equation. So that's what I meant by that you're going to have a restricted set of values that are sensible to solve your problem. And that's going to come from thinking about maybe if you're dealing with a geometric figure and you're talking about volume. Well, we did an example in class where we got h was equal to some expression of x, and then we said, well, h can't be negative, so that means x has to be less than this number. So I'll do another example, but this is going to come from the secondary equation. Secondary. Okay? All right, and then 5, find max or min by taking, I'll say d dx, taking the derivative, and set equal to 0 and solve. Okay? And that will basically get you through the whole problem. So, first problem on MyMathLab. It says find the smallest perimeter and the dimensions for a rectangle with an area of 64. Okay, so let's follow these steps. I think I should be able to fit it right here. So this is number 1. Find the smallest perimeter and the dimensions for a rectangle with area of 64. So write down all my given quantities and quantities I want to find. Area is equal to 64. Okay, now this is a rectangle. So let's draw a rectangle. It says, I said sketch if necessary, or in the book it says sketch if necessary, which you should. So this is, let's say, x, and this is y. Okay? Well, then area is x times y, right? That's the way you want to do it. Now, we don't know if this is our primary or secondary. We're just writing down information just to be able to not be overwhelmed, right? Find the smallest perimeter. Smallest perimeter tells me that I'm optimizing perimeter. Smallest is another word for the minimum, right? So perimeter. Well, perimeter, I don't have it, but I can find an equation for it. Look, I have x and x, y and y, so 2x plus 2y. This is actually my primary equation, and this, so I'll call this 1 and I'll call this 2. Okay. Now let's determine a domain, right? So let's solve this equation. Solve 2 for y. Okay? So in doing that, we get y is equal to 64 over x. Well, that means x, first of all, x has to be greater than 0, right? It can't be 0 because then I'm dividing by 0 and I get it does not exist. It can't be negative because you can't have a length that's negative or a width that's negative. So that's why I say x is greater than 0. That's really all I can say about this at this point. There's really no other, there's nothing else I can say. So let's just use this information. So y equals 64 over x. Okay. So the perimeter is equal to 2x plus 2y. So perimeter is equal to 2x plus 2 times y, which is 64 over x. Okay, let's simplify this down. This is going to be 2x, and let's write it in a way that makes it easy to take a derivative, right? So 2x plus 128x to the negative 1. Now, so we determine our domain where we're here, finding max and min. So how do we do it? This is our primary. So dp dx is going to be 2, and then minus 128 x to the negative 2, set that equal to 0. Okay? Alright, so move the 2 over, and we get 128 over x squared is equal to 2. Alright, and then this is going to be x squared is equal to 64, because we already said that x cannot be 0, so x is equal to 8. Okay? Good. So x is equal to 8. Alright, now it's asking us to find the perimeter, so we need the y value, but look, we have this for y. So that means 64 over 8. 64 over 8 is equal to 8. So y is equal to 8. So that means the dimensions are 8 and 8. And the perimeter is 2 times 8. 2 times 8 plus 2 times 8, which is 32. There you go. So it fits all in a half a page, but it's the process and the thinking that you really have to get through. It's not a super long, it should not be a super long problem. It's more the creativity. So these are the steps. All right. Find the dimensions of the open rectangular box of maximum volume that can be made from a sheet of cardboard 25 inches by 14 inches by cutting. Okay, actually we're not going to do that one. A rectangular plot of farmland will be bounded on one side by a river and on the other side by a single strand electric fence. Okay. So what you have is you have a river. Let's write it like this. You have, okay, you have like a river with nice clean water in it, and then you have this fence, okay, where these two sides we'll say are the same, and we'll call that side y. So then I'm not using any fencing for this side. So you're trying to, again, minimize the amount of material you're using to make this. So you've got 220, so your perimeter is fixed. It's 2x plus y, not 2y, because you see, I'm not using that side, is going to be 2200. Okay? This is my secondary equation. I'm not following the steps exactly now, but it's still, the process is there. I drew a picture. I wrote down some information they gave me. I wrote my perimeter is 2200, and then I figured out how do I express my perimeter as a equation of variables from the picture. Okay. And then my primary equation is going to be what? The largest area you can enclose. So I'm going to say this is area is equal to x times y. Right? Right. Okay. So let's look at the domain here. Y is equal to 2200 minus 2x. Okay. Well, that means, again, since we're dealing with lengths in a real world problems, that means x has to be, first of all, x has to be greater than 0. And it has to be less than or equal to, or less than 1100. Okay? So, you may be able to solve the problem in some sense without doing this, but the issue, and we saw this in class, is that sometimes you'll get solutions when you're taking your derivative and set it equal to 0. You'll get solutions for x and they won't work. And the way you'll know whether or not they work is if they're in what's called the feasible domain. So this is why this is helpful. Sometimes you don't use it because you only get one possibility. But so anyways, now we're going to take this and we're going to plug this into here for y. So we get a is equal to x times, I'll just write it again, and then x times 2200 minus 2x. Okay, so 2200x minus 2x squared. Well, okay, let's do a little fun fact here. This is the expression of a parabola because it's got x squared opening down. So we know that this thing has a maximum. Just a little intuition before we get started. We have an equation of one variable now. We reduced it down to one variable that we need to take the derivative of and set equal to 0. So we do that. 2200 minus 4x, set it equal to 0. And then we get x is equal to 2200 over 4. Which, if I knew math, I could do it in my head. It's 550. Okay? So x, which represents the length of the shorter side, by the way, you want to make sure you plan that out well because it worked out well in this problem, is 550. Okay? Y is 2200 minus twice that number, which is 1100. And there you go. So these are the dimensions that will optimize the area. So we say A is equal to the product of these two. 550 times 1100. A huge number, 605000. 605000. Okay, there's the answer. Good. All right, next. Let's see. All right, this is a good one. I'll do one more here. Suppose Rx, R of x, this is number 6 in your homework, so number 6. Suppose Rx is equal to 288 times the square root of x, represents revenue, and C of x is equal to 9x squared, represents cost, with x measured in thousands of units. Is there a production level that maximizes profit? If so, what is it? Okay, so you have to know a little bit about like business formulas and business calculus, but revenue is the definition is money that's coming in. So I'll write that. Just money coming in. And then cost is money going out. So profit is, at the end of it all, what did you actually make? What did you profit from? What did you keep? So profit, we'll just write profit, is equal to revenue minus cost. So it's going to be this, 288 square root of x minus 9x squared. Okay? So This is actually less work than the other ones because we don't have we don't need a secondary equation because we only have one variable. So the hard part was that you had to think a little bit about the definition of profit and then write it. But look, we already have everything in one variable. So I'll just write this as 288 x to the 1/2 minus 9x squared. So we want to maximize profit, obviously, if you're running a business. So dp dx is going to be 288 over 2 times the square root of x minus 18x, and we'll set that equal to 0. Okay, and so we'll get 288 over 2 is 144, so we get 144 is equal to 18 times x to the 3/2. I just move this over, and then I multiply both sides by the square root of x, and I reduce this to 144. Kind of doing a lot in one step. Okay, and then divide the 144 by 18 is 8. So that we have x to the 3/2 equals 8. All right. Now this you should be able to do this without a calculator. The easiest way to solve a fractional power is to, well, you have to take the, how do I say this? The reciprocal of that power. So like x squared, if I have x squared equals 4, when I take the square root, I'm really applying the reciprocal power, right? 1/2. Excuse me. So 1/2, so we get x is equal to 2. So if I apply this 2/3, then this is to the 2/3. So I get x is equal to 8 to the 2/3. Now we've got to figure out what this is. Easiest thing to do the bottom power first. The third root of 8 is 2. Squared is 4. So x is 4. Okay? Now this is in thousands of units. This is actually 4,000. So really the answer is going to be 4. Well, it's going to be 4,000. 4,000 units. All right? So that's should get you started, and if you have more questions on that, let me know. Have fun.